Thank you for tuning into Dyno Insights. In this episode, Mike and Chris will be discussing sizing the correct dyno for your application.
So far we've talked about the different types of dyno and worked out which technology I want to use. Today I'd like to talk about how we size the dyno to make sure you've got the right size for the engine and the type of testing you're looking at getting involved with. For the sake of discussion, we'll focus on the eddy current and hydraulic dynos today because they have a similar speed and load characteristics, so I think it's probably a good place to start. Mike, perhaps we can talk a little bit about engine types and where we should start off on that side of the equation.
Sure. Yeah, well put, by the way. When it comes to the engine itself, we're dealing with min and max when it comes to speed and torque. So, and it applies to both the diesel markets, the aerospace, motorsports, small engine. They're all going to have these attributes that you need to look at. So you need to know how fast is the engine going to run, up to what its max power rating is going to be or max torque is going to be. Same thing on the other end of the spectrum when you look at the performance of an engine is at the lower end, how slow will you be spinning the engine, and what torque would be required at that speed.
Okay, and from that, we can start to work out how to fit a dyno to meet that engine requirement.
Exactly.
We talk about the dyno similar to an engine in a way in that it has a maximum speed, it has a maximum power where it can absorb power, maximum speed it can run at. But it also has a minimum. And I suppose the minimum, perhaps you could describe it, but it's the lower speed that the dyno can continue to operate effectively.
Yeah, and that's going down the path of when you're spinning and when an engine is spinning, it's not being spun, right? It's driving whatever it's connected to. Unlike the dynamometers we're talking about right now, which are absorbing whatever the engine's producing. So the dynamometers, and let's take the water brake for example, the dynamometer has X amount of speed and water flowing through in it to produce a controllable torque. That means if the engine's asking for a lot of torque at, say, for example, it's producing a lot of torque at...
What's that, around 2,000 RPM?
Yeah, around 2,000 RPM. The dyno, in the sizing it, may not be capable at that point in speed to absorb that amount of torque. It may need to go up to 2,500 before it can achieve that full torque. And this gets into the discussion about, is that the right size? And this is the question that you ask yourself and say, okay, maybe that's not the right size. It may meet the requirement at the high power range and the high RPM range, but it won't meet it at the low end of the range, which you've got to consider these things.
I guess that's one of the challenges as we talk about this, is we're trying to describe something which has a min, a max, both in speed terms, right and left, and a min-max in vertically in terms of the power min and the power max. So should we talk about this in terms of the left side of a dyno curve being the minimum and the right side being the maximum?
Yeah, that'd be a good place to start. And the one thing to mention too is when you look at sizing the dyno for the engine, so we talk about the speed performance, the curve of the power of the engine as it goes up in speed. But when you're sizing a dyno, the obvious factor is you'd like to get in the center of the curve, meaning the sweet spot. So that way it gives you room to move when you're selecting the dyno size to give you additional capability around that point, whether it be on the low end or the upper end.
So you're then talking about what a range of engines rather than having it for one. There might be one ideal spot you can work at. But if we go for the sweet spot of the dyno, there'll be some capacity above that speed, above that load, where the dyno can still work effectively.
Yeah. And one point to mention while you're bringing that up when we talk about this is that a lot of folks sometimes just concentrate on the peak power and peak RPM. And for that application, maybe that works just fine for them. But you got to consider the low end as well as the high end when selecting the right dyno to fit that engine curve, because you're not just sometimes running at the peak end. Now, maybe for performance or small engine work where you're just running a performance curve, then it becomes less critical. But when it comes to points along the way and you're trying to hold a certain point for a duration of time, it becomes important to understand what the capability of that dyno is in relationship to what the engine performance is.
So really we've got to look at this not just as the engine, but also the type of testing we're running to get the full breadth of the requirement. We've got to look at the engine minimum, the engine maximum,
Yep.
but also the type of testing it'll be running.
Exactly.
If it's endurance running at some particular spots, or whether it's doing a sweep across the whole speed range of the engine.
Right. And to give you an example, you may have a test that has to go from 500 RPM to 2,500 RPM in 2 seconds. That would be information that says, okay, in order to go that fast, that quick, I need to understand the performance of the dyno, because you're fighting back the mass of the dyno as you're trying to accelerate the engine. Even if the dyno isn't putting any load on it, you're trying to accelerate past that point to get to that speed in that desired time frame.
Right, so that's not just the performance envelope of the machine, but it's like even the mechanical inertia to be able to accelerate across the speed at the right time.
Yeah, our main focus is not to dive into the minutia, but I'm just illustrating a point that says there's other aspects to consider as you're looking at it. So, and that's just one of them. But the main thing is, sticking to the point of the conversation, is the speed and the power envelopes or curves that we're talking about, how the engine relates to the dyno and vice versa.
So that, in a way, that sounds like you should just go for a large dyno, because then you've got lots of capacity above your chosen speed point. That way, you give you a lot of ability to go to higher power. But would there be a disadvantage of oversizing the dyno?
Yeah, and I can give you an example. So many moons ago, when I was building test cells, I had a specific test that I needed to run. And it's not like you're buying a dyno just for one test, typically. You're trying to buy a dyno that's going to be useful to you for as long as physically possible. So you try to buy a dyno that fits a range in which you may be testing, whether it be engine family or engine sizes. You really want to increase the capability of that dyno or have the ability to be flexible. So in the past, I always thought about that initially about the same thing. So I had a Caterpillar project. It was a water brake application. And I eventually landed up setting it up for an eddy current because I had facilities that wasn't capable of moving that amount of water, and I wasn't going to change the facility design. So there's, again, a decision-making point. But for this conversation, for sizing, I started thinking about, okay, what's the largest dyno I can get my hands on? That way I can test up to that power range. It's more torque range that will give me the ability to test larger engines. The consideration, though, that changed my mind is there's limitations like you talked about. One of the limitations is the inertia to drive that dyno. So if you were trying to run at light loads, it almost became next to impossible with the larger dyno I was looking at to run those light loads, just because of the mass plus the water that needed to run through it. The initial load to overcome was larger than what the engine would be capable of. And then there were speed constraints as well. So as I went bigger up in size, your speed limitations played a factor. So the larger eddy current could not produce the amount of torque I needed at the RPM.
So the risk of oversizing it means we've got to be very selective. I guess it sounds a bit like what we need to do is pick the maximum speed, maximum power, and make sure the dyno is large enough to give you some capacity above your chosen speed load point, but maybe 20% over, 25% over, not sizing it to be 50% or 100% over.
Yeah. Again, it gets back to the point of understanding your test requirements. If you have a specific test that you're making this investment for, or you know this is the business you're in for doing this type of testing, so this could be durability testing, for example, where you're running steady state points all the time, then you could probably get away with a dynamometer that fits a bigger range based upon that type of testing. But if the testing requirements that you do will change and evolve to different types of testing or requirements where inertia becomes a factor, then that dyno no longer is applicable. So you don't have the flexibility. So with every dyno you'll have a certain range in which you can work, which is the performance specification. But you really, if you stay within the sweet spot, then you'll have that room to move on either side to stay focused on in regards to give you that somewhat flexibility.
Right. I guess your local sort of dyno company can help make some of those selections. But it seems for this, the important part is to have a very clear picture of both the engines that you're likely to test and the type of testing you're going to be planning to do. And that the better knowledge you have around that is going to give you the best picture to select a dyno size.
And you bring up a very good point, Chris. The one thing that I can tell you is when I first started getting into dynamometers and test cells, the one thing that I struggled with is the information flow. And that goes both ways. That was information flow from the potential customer. So obviously you have an opportunity and you're going to want to build a test cell or you're going to want to put a dynamometer in. And it's getting information from the customer in regards to the engine performance because you may not know all that information, or specifically if it's a government military contract, you may have limited information. So that was one of the struggles. The other struggle I had was finding a dyno supplier that could work with me with not having all the information, because obviously the dyno manufacturer is going to want to know every last detail that they can get to make sure 100% sure that they've got the right product. And that's the objective, is to make sure that the supplier is delivering the right product, the right dyno to the customer. But you may not always have that handy. So I spent a lot of time talking to various companies and going through the process over and over again just to learn. So obviously the one thing about this podcast is to help people that are listening get to that point without having to go through those gyrations like we did as we built test cells early in our careers and we brought test customer projects in. The one key thing is getting that information or understanding what mattered the most. And that's what we're talking about today. The information that comes to the surface on a high level saying, you must have this. So
right. And perhaps to that point, it seems to me that if you go very much back to basics, then would be the absolute sort of minimum information you'd have to have would be the maximum speed and maximum power. But clearly you need to know your max torque and the max torque speed as well to give those two critical engine points and make sure they fit in the curve of the dyno.
Yeah, in some industries, depending upon what industry you're in, the lower end of it doesn't matter as much as the higher end of it. But from a breadth of knowledge perspective and understanding the performance, true performance of a dynamometer and how it matches up with the engine, it's important to know both aspects of the low end and the high end to make sure that you've sized for your current project and you've protected to size for as many projects in the future and have that flexibility. So we've talked about this before, Chris, in comparing the diesel market, the aero market, which is the turboshaft market for us because it's rotational, the motorsports industry performance in small engine. So all have the same similarities like we talked about earlier, but they do have differences in the market in regards to sizing correctly. But for the most part, what we're talking about today, I think it covers all four, wouldn't you say?
Oh, would, and it's quite interesting, as you say, because sometimes, for example, a small engine will be operating against a governor, so it'll run to a particular load and speed, and that's where it operates most of its life.
Yep, absolutely.
The aero one, it's a very unusual test in that it's going from its idle condition is still a very high speed but a low load. Mm-hmm. And then as it comes onto power, we maintain the same high speed but increase the load. So you have a very different characteristic on the dyno curve that you've got to plot against for those two applications.
Right.
So I think once you know the information about the test and the type of engine, then you'd be working with your dyno provider to refine the questions and refine the dyno selection.
Right. Yeah, good point. And I think the one thing I would want to make sure the audience takes away with them is that when you're looking at your current project, that's one thing. But thinking about, I'm making a significant investment. How do I leverage that investment? What are the questions I need to ask the dyno supplier? Because they'll have questions and they'll probably have more questions back to you than they will have answers initially. But you have to think about, how may I use this dyno in the future? Am I getting the best bang for the buck? All those start at what we're talking about today, but that definitely leads into that conversation where the dyno manufacturer should be able to help guide you, but we're here to help you on the other side of the things of what to expect.
And I suppose it's also to be aware of the trends. It's clear that the engines are getting more powerful. Test requirements are getting more complex. So we've got to make sure you know as much as you can about those limits and the future of those areas to make sure you get the most out of your dyno.
Yeah, that's spot on, Chris, especially when it comes to the test requirements, because you're right. The test requirements continually change. The technology of the engine is part of the driver behind that, because what tests used before are no longer applicable, whether it be because of power, speed, or technology of that specific engine.
Yeah.
So that can't be overstated enough as regards to understanding the testing that you're currently doing.
All right. Thanks, Mike. It's clear that what you don't want to do at the end of this is finish up with a dyno that's too small or too large. So
You got that.
we've got to go through the process. So we talked about sizing the dyno, in this case, the hydraulic and eddy current dynos. I think we need to move on a little bit and cover the AC dyno, make sure we know what's key about sizing that machine.
Yeah, I think it's worthy of a podcast in itself.
It may be, but perhaps we can just talk about it for a few minutes and just see whether the scope takes us that far. I think if we looked at the work we talked about earlier, we sized this for diesel engines, for performance engines, and for small engines, then I think that could apply to an AC also. But there were tests which would take us outside of the AC range, so we've still got the situation where we need to understand the engine, its performance, and the type of testing we're doing.
Yeah, so step one, when we talk about AC dynamometers and sizing it correctly for the application or the customer requirements, we have to consider two things right off the bat. One, keep in mind that this may no longer be an engine. This may be an application where it's an electric motor. So this gets right to one of the key attributes of the AC dynamometer, which is the ability to motor and absorb very quickly. So the other aspect of it is the power or torque. With an electric motor, you can produce 100% torque theoretically at 0 RPM. So if you're testing an electric motor, that's where this becomes typically the only solution based upon those circumstances. So that's part of the selection process for an AC dynamometer.
Yeah, I can see that. And certainly an AC brings about a unique performance capability with the low-speed torque. But it still comes down to understanding, first of all, the engine power and its operating range.
Yep.
But also the type of test you need, because the other two machines we talked about, we discussed the characteristics and sizing the dyno to absorb the power of the engine under test. In this case, we're both specifying it for the power it needs to absorb, but also the power it may need to generate to cover the motoring of the test unit under, for example, emission conditions or fuel economy conditions.
Correct. And again, asking the questions and understanding the test application outside of the test article, the engine or the motor, is you may have to run a test cycle that requires you to run at no load conditions as part of a government cycle that you need to comply with. In order to do this, you have to have something that can overcome its own inertia and give that simulation of zero load capability for the engine operating under test.
So you're talking about a condition where you may be running at a high speed, but trying to simulate zero load. So like a high speed, a very high speed idle condition.
Yep. High or low, doesn't matter. That's the nice thing about an AC dynamometer. It gives you the most flexibility out of all three within its operating range.
Okay, so there with the controls, we'd feed in some power to balance the inertia of the machine. It still comes down to sizing it to the right-hand side of the curve and the upper side of the curve. So the max speed and the max power are probably still the most fundamental sizing elements of this.
Exactly. And again, in our past podcast, we talked about the low end of the curve and the upper end of the curve. You're absolutely correct when it comes to our focus is on the high end, because on the low end, an AC dynamometer pretty much can handle it.
Right. So the sizing job may become a little easier because we're looking at it in a narrower operating situation for the dyno. It's really the maximum size, maximum speed, and maximum power that define the limit of the machine.
Yeah, and this is another differentiator between the three dynamometers, the AC and the other two, is that when you get to sizing it, and depending upon what your budget is, you could theoretically go a lot larger than you typically would be able to go with the other two dynamometers, just because inertia is no longer a factor. So acceleration rates and things like that are still a factor, but less of it with an AC motor or AC dynamometer.
So that brings into the discussion the ability of the controls to overcome the inertia of the mechanical part of this dyno, which, although it can take the load away from the dyno, it then comes into a challenge in how you program it to be a realistic measure of inertia.
Correct. And that, through the algorithms that have been written, mainly contained in the drive cabinets themselves, that gives you that ability to do so.
So does it come down to the definition of the maximum speed, maximum power, and assuming everything else can fit inside the capability of the machine once you've covered those two factors.
It does, as long as you understand the test itself that you're trying to run and making sure that it does comply with that test. And at this given stage in time, we're assuming that the test is understood and it's just a matter of sizing at this point.
But similarly, following the trends we discussed earlier, it's clear that electric motor testing or conventional engine testing with an AC dyno is going to be pushing to higher power and likely higher speed. So it's same thing of making sure we've got enough future proof in the dyno size to make sure we can cover potential future testing.
Yeah, exactly. And like I said, if it were in my hands to buy the dynamometer, knowing the test requirements and knowing the current engine I'm going to test or motor and looking at the future, I would be going for something that has additional capability to run at higher speeds at that given point in time. I don't want to compare it to computer technology because they always say buy the latest and greatest of what you can afford because it's going to change very quickly to the next higher speed or whatever model of a computer. And this technology is not much different. It may be a little bit slower, but it's still changing technology, and the engine industry is changing the performance of our dynamometers by what they're coming out with.
Well, I think it'll be interesting. Perhaps next time we can talk about how controls start to play into the ability of these machines to cover all the test requirements.
Yeah, I think that'd be a good segue into that, Chris.
Okay, thanks, Mike.
You bet.
Thank you for listening to Dyno Insights, presented by Frood. If there are any engine testing topics you'd like us to discuss, we'd love to hear from you. Please email us at podcast@frooddyno.com.